All right, so today we're going to finish up chapter 14. We're mostly going to be looking at applications of simple harmonic motion and some like more physically realistic situations. So there's one thing I just want to clarify first from the previous lecture. On slide 10, I had, after we derived the simple harmonic motion equation for circular motion, so we had just done, our little particle in uniform circular motion, and we got the simple harmonic differential equation here. And then I said where the angular frequency is given by omega is equal to square root k over m. So I just want to clarify that usually we see k only in reference to springs, obviously, since usually we're used to seeing it given as a spring constant. Sometimes you will also see k referred to as the force constant. So even if there's not technically a spring involved, because in our example with just circular motion, there's obviously no spring, you still might be asked for the force constant, which would be k. So you might see k referred to that way. And just to show you that there is a corresponding k for circular motion, even if there's no spring, you might think of it analogous almost to the x component of the acceleration in simple harmonic motion. That's not exactly analogous, but you can sort of visualize it that way as what would play the role of the spring in this situation. And that would be like the x component of our centripetal force. So you can see that if we took the x component, where we had F is equal to ma, obviously, and then we said we have m times the x component of the acceleration, which would be a cosine theta. And then we can just replace the acceleration as we did previously with omega squared times a times cosine theta. And remember also we had a negative sign out here because the acceleration was in the negative direction. And then we have m omega squared a cosine, and now this looks exactly like something of the form negative kx, right? Because this was our x component here, our displacement, and then this would play the role as k. So the force constant is basically that constant in front of the displacement when you have simple harmonic motion. Okay, so I just wanted to clear that up, so now we can continue with the potential energy. So let's get started on spring potential energy. So remember that the spring force is a conservative force. So that means that the work done by a spring is path independent. It only depends on the endpoints, right? Gravity is another conservative force. The electrostatic force is another conservative force. The work done does not matter, does not depend on the path. Friction is your classic example of a non-conservative force because obviously the work done by friction does depend on the path. If you zigzag something around, friction is going to end up taking a lot more energy out of that system than if you just slide it in a straight line. And another thing about conservative forces is that they're always associated with a potential energy function. So you saw this in 7D when you did the electrostatic force. There was a potential associated with that, right? So all conservative forces have a potential function associated with them, and the spring force is no different. And one interesting thing about conservative forces, like I said, is they're always derivable from a potential function. So this you might do if you take, upper div mechanics or something. You'll see that the force is the negative gradient of the potential. Now, if you haven't done gradient yet, or a multivariable calculus, that's okay. In our case, the gradient is just the derivative. So for a spring in one dimension, this is just equal to the derivative with respect to x. So in the case of a spring, we just have the negative derivative with respect to x of our spring potential energy function here. And when we take the derivative of this, we get back our spring force, right? The 2 comes down and cancels out with the 1/2, and then this just becomes negative kx. So we can derive a conservative force from a potential energy function. All right, so that's how our spring potential energy and the spring force are connected. So our spring potential energy, as I said, is 1/2 kx squared. And since with springs we have only conservative forces acting, that means that our energy is conserved, right? Our mechanical energy at least. So our mechanical energy is conserved, which means it's just going to be a combination of our kinetic energy and our spring potential energy. So we have here just our kinetic and our potential. And as long as there's no friction, the sum of these two things will be a constant value in joules. Now I just want to go over quickly the potential energy and kinetic energy in a spring. So let's say we have some spring here, and we've got a little block of some sort, and this is the equilibrium position. Let's say this is its maximum position, the amplitude at x equals a, and then this is its minimum position when the spring is fully compressed back here. So the spring is the equilibrium here, goes out to here, comes back, and it just oscillates between those two. So when it reaches this maximum position here, the velocity is 0, right? So over here, the velocity is 0 because it momentarily stops before turning around and going back. So the velocity there is 0, which means the kinetic energy is 0, right? So the kinetic energy here is 0, and the potential energy then has to be at a maximum because all of the energy has now been converted into potential. So U is a max, and the kinetic energy is a minimum there. Then the same thing's going to be true over here, right? Again, the velocity will be 0 because it's turning around at its endpoint. So the kinetic energy will also be 0 here. And U is another max at that endpoint too. And now in the middle here, so when it's crossing its equilibrium position, the velocity there is at its maximum. So here we have V max. And here, the potential energy is a minimum, and the kinetic energy is a maximum. The potential energy is actually 0. And that's because when it's at its equilibrium position, if you plug in 0 into our potential energy function, obviously the potential energy here will be 0, so all of the energy has been converted into kinetic energy at its midpoint. All right, so that's just an important thing to keep in mind. Make sure that you know very well where the velocity is a maximum, where it's 0, where the acceleration is a maximum, where the kinetic and potential energies are all 0 and maximums for a spring, because on an exam you don't want to have to think about that. You want to just know it right away. So make sure that you really study this and understand where all those things happen. All right, now the next thing. So when we had our spring fully extended, so when, let's say it's out here, and the potential energy is a maximum and the kinetic energy is 0, that means that all of the energy has been converted to potential energy, and we can just plug the amplitude in right here to figure out the total energy. To find our total energy, we have 1/2 mv squared plus 1/2 kx squared. Our velocity here we said is 0, so our kinetic energy is 0, and that means for the potential energy, we plug in the position here at its maximum, which is a, and we get 1/2 k a squared. So that means that the energy at that point is 1/2 k a squared. But since we know that our energy is not changing, our energy is constant, it's conserved, that means that the whole time the energy is equal to 1/2 k a squared. So anywhere you are along this path here when the spring is oscillating, the total energy is going to be equal to this. And then obviously the proportion of it that is made up by kinetic and potential will change, but the total energy is not changing. It's going to be equal to 1/2 k a squared. And we can write that here where our total energy is 1/2 k a squared, and then that's made up partly by the kinetic energy and partly by the potential. And one important thing to keep in mind here is the kinetic energy is always positive, right? Because there's obviously no way for me to get a negative value here. My mass is never negative, and my velocity squared will also never be negative. So kinetic energy is always positive. And in the case of a spring, the potential energy is also always positive. And that's for the same reason. Our k is never negative, and our x squared is always going to be positive. The displacement, even if the displacement is negative, the displacement squared is always positive. That's only true for spring potential energy. You can have potential energies that are negative, right? When we did gravity, I'm sure you came across negative gravitational potential energy. So that's not true in general that the potential energy has to be positive. Just for a spring force, our potential energy is always positive. So make sure you keep that in mind. If you're doing a problem and you get like a negative value for the kinetic energy or something like that, that definitely means you did something wrong. You need to go back and find your mistake. Another thing is that these are both scalars. And they're measured in joules. So this happens more in 7D when we're dealing with the electric field that has components to it. But just keep in mind that your potential energy is a scalar, so it's never going to have components or direction. It's just a single number in joules. Okay, so now let's just do an example with our conservation of energy. So a spring is mounted horizontally on a frictionless table, and a block of mass 0.5 kilograms is attached to the free end of the spring. So this is the same as our problem that we did earlier. So we have our spring here, and we have the mass of it. And we're told that a force of 6 newtons is measured to cause a displacement of 0.03 meters. So this is the same as the problem that we did earlier where we found the spring constant K. So it's the same setup. Now we have the block is pulled 0.02 meters to the right and then released from rest. So it's pulled out to here. This is our equilibrium position. So it's pulled 0.02 meters to the right and then released from rest. So that's its maximum amplitude is at 0.02 meters. What is the block's velocity and acceleration when it is halfway from its initial position out here to its equilibrium position? So we want to know the acceleration and velocity when it is right there. So that's at half the amplitude. We want to find the total energies associated with that position. Okay. So to find the velocity and acceleration, we're going to use conservation of energy first. So we have our conservation of energy equation. Let's write down. We know is 1/2 Ka squared is equal to 1/2 mv squared plus 1/2 kx squared. And we want to find the velocity first. So let's look for the velocity. So we pretty much have everything here except k, but we found k in a previous slide. So if you don't remember, we just did f is equal to kx, and then we just did f divided by x is equal to k, where f was that 6 newtons divided by the 0.03 to stretch it, and we get 200 newtons per meter. Okay, so that was k. So we can just take this was K. And now let's just rewrite our conservation of energy equation to solve for V. So I can see here that all of my 1/2s will cancel. So now I have Ka squared minus Kx squared is equal to mv squared. I'll divide both sides by m. And then take the square root, and I'll get V. All right, so now I can just plug my numbers in. So K, we said, is 200. A is 0.02 meters. Then we have 200 again. X here. So this is the position that we're looking at, which is halfway. That's that A over 2. So we're looking at the midpoint there. So that's going to be half of 0.02, which will give me 0.01. And then we're dividing by the mass, which is 0.5. And when you plug this all into your calculator, you will get 0.35 meters per second. And now you just have to be careful here because the question does ask for the velocity, not the speed or the magnitude of the velocity. So that means you have to worry about if there's a negative sign in front of your velocity or not. So since we started out here, and let's call, this direction the positive x direction, directed towards the right. So since we started out here, and then our block is moving back to the left, that means it's moving in the negative direction. So our velocity is oriented in the negative x direction, so we should really put a negative sign there. All right, and now we want to find the acceleration. So for the acceleration, we can just use our spring force equation where we have F is equal to negative kx. F we know is mass times acceleration. And then to find the acceleration, we just divide by the mass. And then let's plug all our values in here. We have negative 200 divided by 0.5. And the position now is still that halfway point, so we're still at 0.01. And this comes out to negative 4 meters per second squared. And here we didn't have to worry about the negative sign, it just kind of popped out. The reason we did have to worry about it in the previous part where we had the velocity was because we were taking the square root. So we were losing that velocity there, which did not happen here. So, all right, so that's the acceleration. And then we just need to find the total energy, potential energy, and kinetic energy associated with this halfway point. So let's do the total energy first. And this is easy. We're just plugging in values into our equations. So we have 1/2 kA squared for the total energy. So that's going to be 1/2 times 200 times the amplitude, which was 0.02 meters. And this gives us 0.04 joules. And then let's do the potential energy. So the potential energy will be 1/2 kx squared, which at that halfway point is again 0.01. And this gives us 0.01 joules. And now for the kinetic, we have 1/2 mv squared, which is 1/2 0.5, and then the velocity we said was 0.35 squared, and this gives us 0.03 joules. And now a good sanity check whenever you're doing something like this is to always make sure that your energy always adds up correctly. So here we have a total energy of 0.04 joules, and then we have 0.01 joule for the potential plus 0.03 joules for the kinetic, and these two together add up to 0.04, so it looks like we did everything right. Okay, so that's it for part 1, so now we're going to move on to part 2, so today's true lecture. Okay, so as I said before, this is going to be sort of like applications of simple harmonic motion, more physical examples. So the first thing is a non-physical example. So the first thing we're going to do actually is a simple pendulum, which is an idealized pendulum. So in a simple pendulum, we just have a massless string of length L, and it's it's nailed in somewhere up there, so it's pivoting about that point up there, and then we have a little point mass at the bottom here. So for a simple pendulum, we're just going to move our little mass to the side like this, and then let it swing back and forth, and that's going to be our simple pendulum. So does a simple pendulum exhibit simple harmonic motion? So let's find out. So the first thing we're going to want to do is draw like a free body diagram for this case. So we have our massless string here and our little mass m here. And then this is the vertical here. So we're going to have some angle theta here. So we pull out our simple pendulum to some initial angle theta, and then we release it and let it drop. And now it's going to make a little arc like that, right? And now let's see what are the forces acting on this little bob here, this little mass. And you'll see sometimes the mass at the end of a pendulum is called a bob. It just means this little mass here. So we're going to have a tension in the rope, right, going up that way. So there'll be a tension. And then there's just gravity acting on it, right? So we have gravity going straight down. And then that means we're going to have a component of gravity here, and then also a tangential component of gravity there. So this one will be so this will make a little triangle here. And now, since this line and this line are parallel, and this is all one line, that means that this angle here is also theta. So this here is mg cosine theta. This side right here is mg cosine theta. And then this tangential side here, tangential to the motion, is going to be mg sine theta. So this is mg sine theta there. And so what's the restoring force here? Well, the restoring force is this tangential component of gravity, right? Because the tension isn't making the pendulum move back to its equilibrium position. Its equilibrium position is just standing, just hanging straight down like this. So the tension doesn't really do that. The tension just keeps it from falling down. So the thing that's restoring it to its equilibrium position is this tangential force, right? And you can see here that once the pendulum is at 0 degrees, right, once it's perfectly straight down, the component here will be 0 and there'll be no more restoring force. So what we're actually going to do here is look at the torque. Now there's a couple different ways to arrive at the same answer, but we're going to look at the torque here since there is a torque on this little bob at the end here. So the torque is going to be, so the torque, remember, is R cross F. And in this case, we're looking at the torque here from this point. So our length R is just the length of this string here. So R is just L. And then the force is mg sine theta. And here, this line and this line are perpendicular to each other, so we can just take the product here. We don't have to worry about the cross product. All right, and then there's also a negative sign, because if you use your right-hand rule, our torque is pointing into the page because our little bob is swinging this way. So we actually have a negative sign here. All right. Then remember that torque is given by the moment of inertia times the angular acceleration. So torque is given by I times the angular acceleration. And this is essentially the same as our F equals ma, where I, the moment of inertia, plays the role of the mass, and alpha, the angular acceleration, plays the role of the linear acceleration. So I'm going to rewrite this equation with, instead of F equals ma, I times alpha. So we have I times alpha is equal to negative LmG sine theta. And now we look kind of stuck because this doesn't look like our simple harmonic motion equation at all. But remember that alpha, the angular acceleration, is actually the double derivative of theta. So alpha is actually the second derivative of theta with respect to time. So now I can write that in my equation here. So I've got, this looks a little bit better now, right? Because at least we have a double derivative. But now we're still stuck with this sine theta, because sine theta was not in our original equation for simple harmonic motion. So what we're going to do is use what's called a small angle approximation. So the small angle approximation is basically from the Taylor series for sine theta. And it's valid at very small angles, like 10 or 15 degrees, as long as you're less than like 10 or 15 degrees, it's a very good approximation, like within like 1 or 2%. So what we can do, so this is the small angle approximation. And the small angle approximation just says that sine theta is approximately equal to theta for angles less than 15 degrees. So I can just replace my sine theta with theta, and then it looks a lot like my simple harmonic equation, right? So now I'm just going to replace this with theta, and now I just have to write in my moment of inertia for this. So you can use the parallel axis theorem, or like just look it up. So the moment of inertia for this little bob here rotating around this point is just ml squared. So on an exam, I wouldn't expect you to remember the moment of inertia for anything. I never remember the moment of inertia for anything. So I would just give it to you if you needed it for anything. So then we have this equation, and now we can just do a little bit of canceling. We see that our m's cancel, one of the l's cancel, and then we can just rewrite this as d theta dt squared, and then we have just g, negative g over L times theta. So now we have a simple harmonic motion linear differential equation for our pendulum, but only for small angles. So that means that if I took my pendulum and I moved it like to 30 degrees or 60 degrees or something, it wouldn't approximate simple harmonic motion. This is only for small angles, so only if you just tilt your pendulum a little bit, pull it a little bit to the side. Okay, so I know that might be a lot, especially since most people don't remember torque or angular acceleration. We're not really going to be using angular acceleration much, so pretty much, so I would suggest that you know how to derive this. It's always good to know where your equations come from and how to derive them, but you don't need to know really beyond what's here. So as long as you know your general equation for torque, and like I said, I would give you any moment of inertia that you need. So, okay, we have our simple harmonic motion equation now, and now we can equate this right here with omega squared. So, okay, so here is our simple pendulum equations. If you call it, I put x here, so if you call it x or theta, it doesn't really matter. It's displacement from equilibrium, so it's the same thing. So we have here our differential equation for a simple harmonic motion, and here our omega is given by the square root of g over L. So the frequency of oscillations only depends on g, which on Earth will be the same everywhere, and then the length of your pendulum, and that's it. So it doesn't depend on the mass of the pendulum or anything else like that, just the length. And this is still always in radians per second. All right, so let's just do a very simple example with our simple pendulum. So we want to find the period and frequency of a simple pendulum that's 1 meter long on Earth. So the period and frequency, so it might be a little bit easier to do the frequency first. So remember, the frequency is omega over 2 pi. So we can just take, and here omega is g over L. And then we just divide this by 2 pi. So we can just do 1 over 2 pi g over L square root, and then plug in 9.8, and then 1 meter for the length, and we get 0.5 hertz. So that's the frequency, and then the period is just 1 over the frequency. So we have 1 over 0.5, and that will give us 2 seconds. And that's it. So now let's go on to something a little bit more realistic. So this is called the physical pendulum. So a physical pendulum has like an actual shape. It's an extended object. that's going to have a moment of inertia again, but it's still going to exhibit simple harmonic motion if you only displace it a little bit from equilibrium. So we're going to derive that equation again, because omega in the case of a physical pendulum is a little bit different than in the case of an ideal pendulum or a simple pendulum that we just did. All right, so let's look at this pendulum a little bit more closely. Now, this is one of the reasons why I'm not crazy about your book, is because I think their diagrams are like unnecessarily complicated. So let's just look at what's important here. So we have some object that's some weird shape. It has a center of mass or a center of gravity, which in this case is right here. So this CG just means the center of mass. It has what we're calling this length D is the distance from the pivot, so where it's like rotating about, so where it's turning about, from the pivot to the center of mass or the center of gravity is this length D here. And then we have exactly the same components, the same restoring force as we just had, right? We have the mass, the weight is mg. So we have the force of gravity acting as if it's acting only on the center of mass. So we have mg going straight down from the center of mass here. Then we just have our mg cosine theta component and the mg sine theta component, which here is the restoring force, wanting to bring it back to equilibrium. Okay, so we're going to use torque again. So torque in this case, like we said before, is Rf. R here is this length D, because the torque is acting from this pivot point to the center of gravity. So R is D, and then our restoring force is again the tangential component mg sine theta. So then we have the mg sine theta again, and it's also in the negative direction because our torque is directed into the page. And then we're going to do the same thing where we're going to replace torque by I times alpha. So we're going to replace torque by I times alpha. And again, we're going to replace alpha by the double derivative of theta. So we have I d squared theta, and then we have negative dmg sine theta again. And here we can do the same thing with the small angle approximation. We replace sine theta with theta. So let's replace sine theta with theta there. And now here, since this is just some arbitrary extended object, we don't know I. So in the previous example, we knew what the moment of inertia was for our little bob at the end of the pendulum. Here we don't know, so we just have to keep it as I. So now we just have the double derivative with respect to time is equal to negative dmg over the moment of inertia. Oops, no square root yet. And then theta. And now we can equate this here with omega. Okay, so now that's our equation for a physical pendulum. So I just rewrote that here, where in the case of a physical pendulum, omega is given by mgd divided by the moment of inertia. And again, I would always give you the moment of inertia for a problem like this if it was on an exam. And it's very important to note here again that d is the distance from the pivot point to the center of mass. Okay, so let's do a simple example with that. So here we have a uniform rod of length L, pivoted around one end. What is the period of its motion? Okay, so we have a uniform rod here. It has some pivot point there, so it's just like going to be moving like this. And we'll assume it has some random mass m, and we want to know its period. So this is length L. So to find the period, we're obviously going to need to find omega first, right? So omega is mgd divided by the moment of inertia. And here the moment of inertia, again, you just look it up if you're doing it for homework, The moment of inertia here is 1/3 ml squared. And now be really careful when you're looking up moments of inertia, because it depends what axis the object is rotating around. That will change the moment of inertia. So if I have my pen here and it's rotating around this top point, so if it's rotating like this, that's a different moment of inertia than if it was rotating this way. If it's rotating around the center axis here like that. That's a different moment of inertia, and that's again different than, let's say, if it was rotating just around like this, if it was just spinning. Those are all different moments of inertia. So be really, really careful when you're looking those up, that you look up both the shape and the axis that it's spinning around. So in the case of a rod spinning around one of its end points here, this is the moment of inertia. So we can just plug that into our omega formula. So we have whatever the mass is times gravity times d. Now here, d is the length from the pivot point to the center of mass. And for a uniform rod, the center of mass is just straight in the middle. The center of gravity, same thing. So here, d is just L over 2, right? It's just halfway. And then I, we said, is 1/3 ml squared. So this gives us, m's cancel, one of the l's cancel, and we're left with 3/2 g over L for omega. And then the period is just given by 2 pi over omega. So we can just do 2 pi divided by 2/3 L over G square root. So I just put omega in the bottom here. And this is our period. Now let's say that the rod had length 1, like in our previous example. So let's just say if L is equal to 1 meter, just plug in 1 here and 9.8 there, and we would get the period is 1.64 seconds. All right, so that's it for pendulums. Now let's look at a different type of oscillations that's more physically realistic, called damped oscillations. So normally when we have like a spring going back and forth, it's never really frictionless. There's never really no air resistance or anything like that. So we normally have dissipative forces, and friction or air resistance are both what's called dissipative forces. So when we have a object that's undergoing simple harmonic motion, but one of these dissipated forces is present, it's undergoing damped oscillation, which means it will eventually lose its energy and stop oscillating. So and these dissipative forces are called damping forces, and a damping force is directly proportional to the velocity of the object. So our damping force will just look like this. It will be negative. Remember, just like friction is always opposing the direction of motion. So it's negative the velocity and then just times some constant. So now we can rewrite our simple harmonic equation and include this force in the net force. So now we have our damping force here and the spring force. So this makes our differential equation look like this. So now we have this extra term here. So solving a differential equation like this is a little tricky, and it's definitely beyond the scope of this course. You need to take like a differential equation course for it. So I'm just going to give you the answer. So the solution to a simple harmonic motion with a damping force is given by this. So it looks similar to our solution before, where it's just the cosine omega t, but now we have this extra exponential here. So we have this e to the negative some constants times time. So you can plug this solution into this equation and again find the frequency. So we don't have to do that. Again, I'll just give it to you. So this is the frequency of oscillation that an object will have if it is being damped. So notice that this frequency is going to be less than if it was undamped, right? Because normally we just have square root of k over m. But now we're subtracting this extra term here. So that's going to make the frequency a little bit less than if it was undamped. And what this exponential term will do here, so let's say if it was so let's say we have, this is t and this is x. So what it's going to look like is like this sort of. So your amplitude will get smaller and smaller as time goes on. And so this here is like your cosine, right? This is like the cosine omega t. And then we have this exponential function kind of hugging it. So this is the e to the negative b 2m times time. So we have this exponential function that's squeezing our cosine together and making the amplitude decrease with time. So as you can see, eventually as time gets to infinity, our system will just stop oscillating. Okay, so here's a picture just to have you see some different kinds of oscillation. So here this blue line is some weak damping. So our damping force is not very strong, and you can see that it continues oscillating for quite a bit. Now compare it with the stronger damping. So when you have a stronger damping force, it stops oscillating pretty quickly, right? This one kind of tails off pretty fast. And now there are a couple of different types of damping. So we have this omega is k over m minus b squared over 4m squared. So there's a couple different things that can happen here. The first thing is that omega can be positive, right? So if omega is positive and your system is oscillating like this, that means that k over m is greater than b squared over 4m squared. This is called underdamping. So if this is the case, we can simplify this a little bit. We'll get 4mk is greater than b squared, which will simplify to b is less than 2 square root km. So if this is the case, omega will be positive, right? Because that means that this term is greater than this term, so it's not imaginary or anything like that. And then you will have it just oscillate like this. Now, what if these two terms are exactly equal? So your omega then is 0. So if k over m is exactly equal to b squared over 4m squared, that simplifies to this. And this is called critical damping. So critical damping means that your system won't oscillate at all, right? Because omega is 0, so that means it's not oscillating. So it just means that as soon as you let your object go, it'll just immediately go back to its equilibrium position without oscillating at all. Then we also have what's called overdamping. So we have one more option here for our parameters. What if this last term was actually bigger than this term here? Then that would give us a negative underneath this square root, which would give us an imaginary omega. So if k over m was less than b squared over 4m squared, that means that b is greater than 2km. This is called overdamping. And again, since our omega is imaginary, we can't oscillate with imaginary frequency. That means that our system doesn't oscillate. And it just basically goes back, just like with critical damping, it just goes right back to its equilibrium position. It just takes a little bit longer to get there than in critical damping. So I just wrote these all down here. This is exactly what we just went through. So if we have a damped system, we can keep it oscillating by applying a force to it. So this is called forced oscillations, and we apply what's called a driving force with a driving angular frequency, omega d. So that just means that we're going to apply some force to keep our system oscillating, and it won't lose all of its energy to friction or air resistance. And a good example of this is like pushing a kid on a swing, right? If the kid starts going, eventually air resistance will make them stop, but you can stand there and push them, right, with some frequency, and they'll keep swinging as long as you're pushing them. So in that case, you're the driving force, and you're swinging them with some angular frequency, omega d. And now one thing that can happen with forced oscillations is what's called resonance. So resonance happens when the driving frequency is close to the natural frequency of oscillation of your object. And what can happen is that you can get this huge peak in amplitude if your driving frequency and natural frequency are close. So if the parameters are right, you can get this huge spike. And this has happened in like earthquakes where the buildings were built to have some natural angular frequency, and then the earthquake has that same frequency, and then the buildings basically get this huge spike in amplitude in how they're oscillating, and they collapse. So we're not going to do much more with resonance than this, but it's good to just know what it is in case it pops up again. Okay, so now we're just going to do a couple more examples and also just some miscellaneous things that I know trip some students up. So the first thing is Taylor series, obviously. So I know when I took calculus, like we learned what a Taylor series was, but I had no idea how to use it or like what it was useful for, and I thought that they were just kind of like useless. But they're actually used a lot in physics, and a lot of problems are not solvable unless you use a Taylor series. And another thing is that physicists are notoriously sloppy with our math notation and just our math language in general. So when I say Taylor series, what I really mean is a Maclaurin series, since a Maclaurin series is technically evaluated at around x equals 0. When we say Taylor series in physics, we mean a Maclaurin series. So a Taylor series is just a way to approximate a function when it's very close to 0. And there's a great video by 3 Blue 1 Brown about Taylor series. If you don't know about the YouTube channel, you don't watch it, I highly, highly recommend it. He has great like visualization for different concepts in math and physics, and he has a really good video about Taylor series. So I highly recommend you watch that video. So some common Taylor series that you're going to see a lot in physics are sine, cosine, and the exponential. So the sine function is expanded this way, and these terms go all the way out. There's infinitely many terms. But typically we only care about terms up to order 2, which means terms up to x squared. So in the case of sine, we have x, and then there's no x squared term, and our next term is x cubed. So when we're at very small values, like 0.01 or something like that, 0.01 cubed is so small, it doesn't really add anything to our approximation. So that's why we usually only keep terms up to order 2. So in the case of sine, there is no order 2 term, so that's where our small angle approximation came from. We just took the first term in our Taylor series and said that's what sine is equal to when we're at very small values close to 0. And like I said, that's accurate to within like 1% of the true value, so that's good enough. Another interesting thing here is notice that all of the terms here, all of the powers are odd. And that's because sine is an odd function, right? When you graph sine, it looks like this. So sine is an odd function, so all of the terms in its Taylor series are odd. And now cosine, you will often see just this part, so if you only care about up to order 2. So cosine is frequently approximated as 1 minus x squared over 2. And again, you will notice that all of the terms here are even. And that's because cosine is an even function. So all of its terms in the Taylor series are even. So it looks like that. Kind of. And then another very common one is e to the x. So e to the x, usually we just approximate, even just with these 2 terms, is usually good enough. And this one pops up a lot in physics. And this has all terms, has both even and odd, because e to the x is neither even or odd, right? It just looks like that. So that's not really even or odd. All right, so let's just do some examples to get a little bit more practice. So here we have a student studies a pendulum by graphing the angle theta that the string makes with the vertical as a function of time. We obtain this graph here, and we want to know first the period, frequency, angular frequency, and amplitude of these oscillations. So to find the period, we just have to look how long does this take to complete one full oscillation. So one full oscillation will be from here to here. So we just have to see how much time this takes. Each of these boxes, we have 1, 2, 3, 4, 5. So they're each 0.2. So we have 1, and then 1, 2, 3. So we have, this is at 1.6. So the period is 1.6 seconds. And then the angular frequency, let's do the frequency first. So the frequency will just be 1 over that, which will give us 0.625 hertz. And then the angular frequency will just be 2 pi times the frequency. So we get 2 pi times 0.625 is equal to 3.93 radians. And then we need to find the amplitude. So the amplitude, we just have to look at how high up does this graph go, and we get 6 degrees. So the amplitude is 6 degrees. Now it's important to be careful here because we have both degrees and radians in the same problem. So our amplitude, or our graph here, is in degrees because it says so. But when we calculate the angular frequency, it's still in radians because angular frequency is defined in radians. So when you multiply your frequency here by this 2 pi, there's like a hidden little radians in there. So it's okay to have part of our answer in radians and part of our answer is in degrees here. That's totally fine. All right, now we want to do part B. So how long is the pendulum? So the pendulum, the pendulum's length we can find with our equation for omega. So we know omega is g over L square root. So we can square both sides. We get g over L. And then solve for L. We have L is equal to g over omega squared. So just plug in 9.8 and plug in 3.93 squared. And you end up with L is 0.635 meters. So this is the length of our pendulum. So is it possible, now for part C, is it possible to determine the mass of the bob? So no, it's not. And the reason is that you'll see the period, the frequency, they all depend on omega, and omega only depends on G and L. And the amplitude doesn't really help us with the mass either. So there's no way to figure out the mass from the information given here. So it's not possible to figure out the mass. All right, now let's go on to one more example. So here we have two pendulums. Each have a solid uniform ball of mass m supported by a massless rod. And the ball of pendulum A is very tiny, and the ball for pendulum B is obviously much larger. So we want to find the period of each pendulum for small displacement, so when they're undergoing simple harmonic motion. And we also want to know which ball takes longer to complete one period. So the first one we can just treat as a ideal pendulum since it, this essentially has no radius. It's a perfect ideal pendulum here. So we can look back at our previous equations for pendulum A. The period of a simple ideal pendulum is 2 pi L over G. We just get that from omega is equal to square root G over L. Okay, so that's all we can do so far because we don't know the length, and that's really it. So now let's look at this larger one. So for pendulum B, remember that the frequency for a physical pendulum is mgd over the moment of inertia, which means that the period here will be 2 pi times I over mgd square root. So we need to figure out I first. So the moment of inertia for this ball, again, I would just give this to you on an exam because you need to look up the moment of inertia for a sphere and then also apply the parallel axis theorem because it's spinning some distance away from itself, right? So our pivot point is actually up here. So I would just give you that moment of inertia. I don't expect you to remember the parallel axis theorem. So the moment of inertia for this is I is equal to 11 over 10 ml squared. And that's for a sphere rotating around a point a distance L away from its center. Okay, now we have to figure out D. So D, again, is the distance from the center of mass, or the center of gravity, to the pivot point. So that means that this is D. And we can see that that length is clearly L, right? So D is equal to L. And then we can plug that into the period formula that we had. We have 2 pi 11 over 10 ml squared divided by mg L. And then we get 2 pi. Let's see, our masses cancel, one of our L's cancel. We get 11 over 10 L over G. All right, so we can see here that this period and this period are almost the same, but we have this extra factor of 11 over 10 in the larger ball. So the square root of 11 over 10 is going to always be greater than 1, no matter what L and G are here. So this period is always going to be larger than this period. So that means that our period for ball B is going to be greater always than the period of ball A. Okay, and then there's still one more thing I want to just quickly clarify since simple harmonic motion is so important, and I'm sure you will be seeing this again. So our equation for simple harmonic motion, we said, was this. And I said anytime you see this equation, that indicates that your particle is undergoing simple harmonic motion. And what's really, really important here is that it has to be negative. So we have to have this negative sign here. If I had an equation like this, let me use a different, let's say L. This is not simple harmonic motion because it doesn't have the negative sign. And the reason that is that the solution to this equation and the solution to this equation are very different. So here, a function that solves this differential equation are sine and cosine. So I could have sine omega t or cosine omega t. Both of those functions solve this differential equation. So let's take the first derivative, let's say of sine. The derivative of sine is negative cosine omega t times omega. And then we take the derivative again, we get negative sine omega t, and then we get an omega squared. So we have x double dot is equal to negative omega squared x, right? Where this was our original function x, and this is the second derivative of it. So when you have sine and cosine, you always will get this extra negative sign here, right? No matter if you start with sine or you start with cosine, you're going to get a negative sign here. And this makes sense because sine and cosine are periodic functions, and we expect something undergoing periodic simple harmonic motion to have a sine or cosine represented, right? Because that's basically the definition of periodic. Now, in this case, when I don't have the negative sign, the solution to this equation is an exponential. So here, my solution will be like e to the lt. So if I take the derivative of this function twice, so I'll get L times e to the LT, and then the second derivative will be L squared e to the LT. Now I have, this is positive, and then this is my original function. I'm just replacing with x here. So now I didn't get a negative sign, right? Because there was no negative sign here. And e to the LT is not periodic, right? So e to the, my exponential function looks like that. So that doesn't look like simple harmonic motion. So the solution to this is not a periodic function. And that's why it's so important that you have this negative sign here when you're looking at an equation that might be simple harmonic motion. Because only periodic functions are the solution to this, and no periodic function is the solution to this. So, okay, like I said, you probably won't be, I'm not going to test you on differential equations like this, but you will definitely see stuff like this again, I'm sure, whether you do engineering or a physics major. So it is important to keep that in mind, the difference between the periodic and non-periodic functions. All right, so that's it for chapter 14, and I will see you guys next week.